Unmuted.
Hello, everyone, and welcome to today's SANS webcast, Cybersecurity Strategies, Protecting Your ICS Investments, a discussion with Ultra Electronics and Mike Asante of SANS. My name is Keaton Nguyen, and I'll be moderating today's webcast. Today's featured speakers are Mike Asante, Director of ICS at SANS, and Alex Charter, Technical Director at Ultra Electronics. If at any time during the webcast you have any questions for Mike or Alex, please enter them into the questions window located on the GoToWebinar interface. We will be answering them during the Q&A session at the end of the presentation. And with that, I would like to hand the presentation over to Alex Charter.
Muted.
Today we're going to talk a lot about end-to-end cybersecurity, and I'm very grateful to be joined by Michael Asante, who's the lead instructor for the ICS SCADA Security at SANS. If you've never taken one of Mike's courses, I highly recommend them. They are excellent and a very, very knowledgeable person in this area. Myself, I'm from Ultra Electronics 3TI. If you've never heard of Ultra Electronics, that's because we do aerospace and defense. We're an aerospace and defense company. Oops, sorry, just trying to move the slide forward and having a few issues. There we go. Thank you. We're an aerospace and defense company who operates around the world, pretty much creating niche solutions for different customers, be those aircraft landing gears, sonar buoys, nuclear reactor temperature sensors, cybersecurity for industrial control systems, airport baggage handling systems, you name it, we do it. But here at Ultra 3TI, which is where I'm based, we focus primarily on connecting, protecting critical operations. That's enabling secure communications and protecting from a cyber and physical point of view, critical infrastructure and facility management. So what we really want to talk to you about today is ICS cybersecurity and the need for end-to-end cybersecurity. This is not something that should just happen within the enterprise or on PCs, but we need to take it all the way down to the embedded end. That's all the way down to the PLCs, the meters, the sensors, or the equipment. So we'll go over some of the risks and why you'd want to protect these systems, some of the vulnerabilities everybody's familiar with from the enterprise side, and then introduce and help make available some of the vulnerabilities and how you can go about mitigating some of the risks to those embedded systems. And finally, we'll provide some recommendations. It's not all doom and gloom. There actually are ways you can go about solving it, so we'll provide those. We'll provide you some simple things to take away. These presentations can be long and complex, and sometimes you forget what you heard at the beginning, so we'd like to wrap it up and give you a few points to really hit at home and help you take away those things. So here's where we all know. We all know an industrial control system is mainly comprised of external networks, business networks, connecting into a support network, connecting into production control network, all the way down to the PLCs at the far right. But if we flip it around and look from the bottom, really the PLCs and the industrial control equipment interact with the real world. And all of the commands, all the instructions they're given, and all the sensor data they produce go back through the process control network up to the HMI and engineering terminals. And this is how it's been for a long time. It's only been relatively recently where we started to realize that we need to incorporate some more sense and monitoring data, some business equipment, business intelligence into this system. If you're running a power station, you need to know how much raw material you're using so that the business can order more. If it's a coal plant, how much more coal do you need? Or how much CO2 did you produce? Or how much power did you produce? So all that information needs to leave the process control network and get out into the external, the business networks. And you do that normally by interfacing through a support network. So today, we're going to talk a lot about the far right-hand side, the embedded devices, all those elements that really operate either on a serial bus, serial to IP networks, and how they interact with the PC networks. And especially when it comes to cybersecurity, we tend to initially focus entirely on the purple area. we're very concerned about viruses, external connectivity, all of those elements that really interact with the purple domain. But what we want to do today is really push down into the far right, into the orange domain, and show you why it's so important that you can't forget about these areas. So really, what are the risks? What are the reasons why you should protect them? Well, protection is risk management. And risk management is all about identifying what you want to protect, knowing what you want to protect those assets from, and then know what you're willing to protect them against. Know what your threats are. If you can't identify each one of those three elements, then you can't adequately perform a risk management activity. So if you want to sort of go through them one by one, really, what are the impacts, what are the objectives? We're pretty sure what we know about our assets. What do we want to protect? Well, they're the things that we've actually spent a lot of money purchasing to begin with. They're all the control equipment. They're the enterprise PCs. There are our employees, our company reputation. It's anything that we've invested money, time, effort in. But really, what are the impacts? What do you need? Why should you protect them? Well, they're the classic ones of you don't want to introduce, you don't want to harm the reputation of the business, you don't want to harm anybody physically from a safety point of view. But really when it comes to cyber, there are sort of four main areas that people concentrate on. One is denial of view. If I can't see from my HMI exactly what is going on, and I don't see what the current situation is, I can't make adequate decisions. So that's a denial of view. Denial of control is I can see exactly what's going on, but I can't do anything about it. No matter what button I press, no matter what big red lever I pull or button I press, nothing happens. The other more nefarious ones are really manipulation of view, manipulation of control. When you think you are seeing something, or when you think you are doing an action, and what you think you're doing or think you're seeing is not actually the case, then you're making bad decisions. You're making decisions based off either bad data or what you think you're doing is not actually what is occurring. And this can have a really big safety impact as well as just a business operational impact. If you're operating less efficiently than you assume, you're not making as much money. You're not meeting your performance objectives. And that can have a negative impact on just your employment and your company's business. So what are the threats? What do you need to protect yourself against? Now, we're used to sort of thinking out, well, we want to protect it from cyber attack. But what I'd like to introduce you today with is the three different families of threats. And this is something that's sometimes a little convoluted, and sometimes they're all lumped together, but it takes a bit of time. It's well worth sort of ensuring that you can identify the different types. One of which is the non-targeted, non-ICS specific threat, cyber attacks. These are the generic viruses, worms, configure, slammer. We're all familiar with those which are not going after any one industry in specific. They're not targeting one type of industry, and they're not even targeting you as an individual or you as a business. It's just a background infection that tries to take over everything. The second type is targeted but non-ICS specific. That is, I want to go after you specifically, but really I'm not going after your industrial control equipment or industrial control systems. I'm going after your business system. So just because you happen to be operating in the industrial control sector, I'm going to attack you, but it doesn't mean I'm actually going after your industrial control systems. And then the final one is those which are targeted and ICS specific. That is to say, those ones where we are specifically targeting you for who you are, and we are going after your exact ICS systems. So we're actually taking it all the way down and attacking your industrial control equipment. So I'd like to, have you think in the back of your mind all those different types of threats, and to not necessarily join them together and assume that any one protection, if you're trying to protect yourself against a targeted and ICS-specific attack, that you forget about the non-targeted, just the background noise. Or if you think you're well protected against the background noise, you haven't considered all those definitive targeted and ICS-specific attacks. And I should say that really, there's not a lot you can always do about this. I mean, if protection is really risk management is about reducing your risk. You can't always do a lot about the threats or the impacts. The impacts are what they are. If your business shuts down, it shuts down. You lose money. If your business, if your industrial control equipment crashes or goes crazy, it can have a safety impact. There's not a lot you can do about those. There's not a lot you can do about the threats. The threats are there regardless of what you do. You can try and be neutral, you can try and be Switzerland in this world, but ultimately somebody will still come and attack you. Therefore, risk management is pretty much boils down to vulnerability management. It's about trying to reduce the vulnerabilities, not necessarily reducing the threats or impacts. And I should point out that vulnerability management is not attack vector management, and those things are slightly different. Attack vectors are trying to mitigate the previous attack. So if somebody's attacked you because they've managed to infect a USB stick and you plug the USB stick into your computer, an attack vector management would say, all right, no more USB sticks. Well, it wasn't the USB stick itself. It was malware on the USB stick. So really you should try and prevent unauthorized programs from running, not necessarily banning USB sticks. So we need to think, and it's always sometimes easier to go after the attack vector than it is the underlying vulnerability. And to help articulate all of this, I'd like to hand over to Mike to really go over how this operates in the real world and how some real-world examples help articulate this. So Mike, over to you.
Thanks, Alex. I really appreciate it. I'm very excited about today's presentation here on two dimensions. One, I really like the idea that we're going to focus on the embedded system side. We're going to get into that orange zone of the model that Alex presented earlier. The second exciting element here, from my perspective, is just this general model of looking at the world of non-targeted, non-ICS specific attacks, and targeted but non-ICS specific, and then targeted with ICS specific capability. I think that's a very useful and practical model. It helps define the use cases, if you will, that we'd like to use for everything from looking at risk within the organization, understanding exposures and where vulnerabilities might lie to be exploited in these different scenarios, and also helping us to prepare and plan for each one of these things playing out, because the impacts will be different. And also it's important to note, and my general feeling about this, and I'm about to walk through a couple of real world cases to kind of back this up, but non-targeted, non-ICS specific attacks like Configure, Slammer, Worm, they were really the impetus and generation for a lot of the ICS security models that we have in place today. If you look at the standards themselves, most of them were informed based on the early 2000 experiences to later 2000, where Slammer was a big concern. It did affect lots of industrial control systems. I was a chief security officer at the time, and we certainly we were able to keep them out of our production environments, but it was a very real concern. Configure did actually find its way into control systems. We'll talk a little bit about how it did that and what the impacts were. But again, they were never designed to be there. They were never designed to have a specific effect. They found their way there, typically because of poor architectures or practices on our part as end users. And I call these, in these cases, non-structured, non-targeted attacks. They clearly were not designed to be ICS capable. And these attacks, we do a generally good job with our current security regimes of having logical segmentation and enforcement zones and security zones in our models. If you look at the second element, which is that targeted but non-specific ICS attacks, those attacks themselves can be concerning because they can actually provide you with information, and it leads an end user to ask themselves, what information would allow somebody to take the next step and actually conduct a targeted ICS attack? What information exists or credentials exist in my IT enterprise that could be collected and used by somebody else to actually conduct the last type of attack? So with that, let's specifically look at Configure Worm. I want to break down, if you will, I'm using the Lockheed Martin kill chain that they modeled. And if you look at that, stage one, if you look at Configure, it wasn't really targeted. We're not sure what the malware authors were doing relative to reconnaissance and targeting. It's very clear that they were exploiting a specific vulnerability. They were looking at infecting internet-facing or connected systems. They did create network propagation capability within the worm itself, so Configure could spread once it gained a foothold within an enterprise environment or any type of network. And then from there, they did have established command and control and some nice sophistication to how they actually try to communicate with infected machines. Configure would be a classic IT attack that actually did impact ICS systems. How did it do it? mostly through, and this is, at the time frame, we didn't have that many internet-facing systems. There certainly were some. But in many of the cases I'm aware of that we looked at, it was because of remote access. At the time, there was remote access from a network that had gotten infected, and the machine that was being used to establish the remote access was actually infected with a configure. It used its propagation features to move across that remote connection into the environment. And if you were connected in a network that had Windows-based operating systems, in that case, most of the cases I'm aware of were all Windows-based control elements, they too were infected. Now, many of the impacts and effects weren't specific. It's what came with that worm. One, the attempt to propagate meant you had lots of data storms on the small networked environments. That caused some trouble. In some cases, some of the events, the devices were remote devices that were using VSAT communications, and when they were trying to communicate, configure kept initiating communications to try to propagate or to command and control, and those initiations were running up bills for the satellite service. And in other cases I'm aware of, when I was the director of the ISAC, configure did make its way on auxiliary control systems within plants. And again, I think it's because at the time, the architectures had holes punched in them through remote access where already infected machines moved across, and there was no endpoint security in these control devices. So this is a good example of where an IT-based attack affected control systems. Now, just to put a little finer point on Alex's great presentation about impacts, or functional impacts, what I like to call. In our SANS classes, we teach this kind of model here about kind of three major categories, and Alex covered all of them: loss, denial, and manipulation. Loss of view and loss of control was covered. You did a great explanation of that. There's also this idea of denial, where I can actually, they sound like they're the same thing, but you can actually force the view. It's not that you're removing the view, that you're causing a view to be intermittent, for example, graying out HMI screens as a quick example. Denial of control, where I can't actually physically control because I've denied you from being able to send a command signal, for example. Or denial of the safety system, which has even greater implication where the safety system will act. And then finally, Alex talked about manipulation, and I would extend that to include manipulation of the safety system, where you change set points. So the safety system is now triggering off a wider envelope that would allow the attacker to achieve some type of goal where the safety system would have actually prevented that if the safety system had not been compromised by the attacker. And also consider manipulation of sensors and instruments. When you think about control systems and functional impacts, one of the things an adversary or attacker might do is try to trick the system. One of the ways you could do that is to provide bad data coming from sensors and from instruments within the control system itself. So I think that's a great functional model for considering potential impacts. The next view is a specific attack on ICS. So this is the third category where the attacker really is looking to get not only a foothold and move through a path that gets them into a production environment, but they're prepared to take the information that they can gain access to, turn back around, develop a specific capability or effect within the control system, and then deliver that effect and launch that effect for this outcome. And a great example of that would be the recent German ironworks incident, which BSI reported on. Now, BSI reports were limited in the details that they provided. We've had discussions with BSI representatives, and they're aware that this incident, hence why they made it public, is significant. And hopefully we'll be able to learn more about the incident in specific details. But in this case, it's a great example of a multi-stage steps. Stage one is traditional kill chain, where there clearly was reconnaissance and targeting. In this case, they suggested it was spear phishing, where spear fishes were sent with executables that allowed the attacker to gain a foothold. Then the attacker did pivot. They weren't specific about what those pivots look like into a production environment, so they're able to collect enough information or credentials to get themselves into a control system environment. From there, they did say the attacker demonstrated good knowledge of the ICS, and so the attacker was able to develop, we're not sure if they tested, but they certainly developed and delivered a capability, because the end effect was damaging equipment under control, in this case a furnace. I don't know if it's an arc furnace or a blast furnace, but the report suggested they catastrophically failed the furnace. So they had an effect, and that really meant they were able to control the system or manipulate it in a way that the end user obviously would not want to have done. We don't know how the safety system, or if there was safety system logic, and how that interconnected with the control system. Those are great details for us to learn, but this is a great model and example of an ICS capable attack. And you can see in the multi-stage kill chain, the attacker was certainly doing all the different steps to get to an outcome or effect. With that, I think it's important, and as Alex noted, we are capable, defense is doable. And if you look at these 3 different use cases and we make sure that we're comprehensive in how we think about how we protect assets all the way down to the embedded system level, we can seriously make this a very difficult enterprise for the attacker. And in this chart here, I want to make it very clear that there are some easier type of attacks, like getting malware into a control system, and that would be a compromise of ICS security. We have lots of those, unfortunately. However, it's extremely difficult to develop an attack that has high confidence, meaning you have a very predictable outcome the attacker is trying to achieve, and you can cause that effect. That is a very difficult enterprise in that you need information on the configurations and controls. You need to understand the control system. You need to be able to operate in a manner that's effective, meaning you can get your effect to occur and not knock the system over or exceed its capabilities when you do that. And so those are extremely difficult. So if you think about this model, you can start planning your defenses to try to push everything into the, to make it more difficult for the attacker. And with that, I'm going to turn it back over to you, Alex.
Thank you very much, Mike. So at this point, we'd like to take the opportunity to ask the group a poll question, which is basically, do you perform risk management or vulnerability assessment within your environment? In all these cases, we talk about this, but not as often a case do we actually perform it. So in thinking through what Mike has been talking about and what I've been talking about in terms of identifying all those assets, identifying the impacts, identifying the threats, and performing a risk management activity. If you could take the opportunity to now vote and choose one of the applicable options if you perform risk management or vulnerability assessments. So we'll give you a few minutes, we'll give you 30 seconds, and then we'll collect the results and move on. Okay, I think we have it settled down now. And so as a result of that, what we find is 56% of you have said, yes, regularly we perform risk assessments, and 24% say, yeah, at least once a year. But what's interesting is we do have at least 21% of respondents who either don't plan on doing it or don't think it's needed. And this is still a quite common view. So there's nothing inherently wrong with that position. But what we'd like to do is explain a little bit more about why we think risk management is necessary, and if, when you're doing it, what you should take into consideration. I'd like to sort of take the opportunity to talk a little bit about the Sony hack. Sony at least sat down, the Sony executives sat down and said, you know what, we don't think we need to spend as much money on cybersecurity solutions because we don't think it's that big a deal. And they made that business decision in full awareness of the facts, and you know what, they got it wrong, but at least they made that informed decision. And so I think that's always a good thing. There's nothing inherently wrong with saying, you know what, I make an informed decision, I don't think I need to do a risk management activity, or I don't think it's useful. But I always advise at least make that in the full awareness of all the facts. So what we'd like to do now is discuss a little bit more about what are the vulnerabilities and some of the potential mitigations, and help identify, are these things that you're considering when you perform your risk management activity or not. So the first stage I'd like to talk about is the enterprise vulnerabilities and mitigations. So in this section, as I say, I'm talking a lot more about the PCs. So in the first one that everybody's very familiar with, and we'll go through these very quickly, remote access. The idea that your power station, your industrial control equipment, whatever, is connected to the internet. Why? Because somebody from a more public network can gain access directly into a critical internal system via a remote connection. And the way mitigations that people normally use is one of three. They either use next-generation firewalls, data diodes, or VPNs, which are all very, very good solutions, and all of them we would advise, as long as you know the impacts of what's going on. So next-generation firewall is great. It helps narrow down exactly what is allowed through. However, it doesn't do so well if the traffic is encrypted, nor does it provide any authentication. So while it may allow a command through and say, yes, that is definitely industrial control protocol, I still don't know, the firewall won't know exactly who it came from, or if that's a legitimate action or a malformed packet or anything like that. A data diode, on the other hand, will only allow through legitimate or otherwise well-formed packets, but it does limit capability because it can only necessarily travel one way. So although you connect it to a more public network, information can flow out into the public network, but information from the public network can't necessarily flow back in. And then VPNs are a great way. They are a tunnel. If you think about an encryption provides a tunnel. It stops anybody from outside being able to come in, but anybody on the inside can communicate freely. So a VPN will stop anybody from outside coming in, but it will encrypt malware just as easily as it will encrypt legitimate data. So essentially with a VPN, you have to trust all the computers sitting behind it. So that's why if you have remote access for a contractor coming in, or you have remote access from a vendor, you have to essentially trust, even though it's a VPN connection, you have to trust every computer within that vendor's infrastructure. So what about enterprise? What about a malware infection? So if you think about ignoring remote access, if you've successfully disconnected yourself from the public networks, or you have good good protection to mitigate any attack coming over that, you still have to worry about local infections, where somebody can come in and plug something into your engineering terminal and infect your system with malware. The way that people normally mitigate these is really going through and using antivirus, disabling external ports, or potentially just air-gapping the system entirely. And so when you look at these sort of styles of solutions, what you can say is, yeah, they're pretty good at preventing non-targeted, non-ICS specific attacks. If your antivirus is set up to identify well-known viruses or worms such as Configure, it should be able to mitigate that. When it comes to targeted but non-ICS specific elements, it's less effective. It can be good, it can be bad. So some of the well-known remote access Trojans, it can be antivirus has a pretty good track record, but anything new, any new vulnerabilities coming out, any new undetected targeted attacks won't be picked up. So you have to assume that those will still get through. And then, of course, anything which is targeted and ICS specific isn't necessarily going to be attacking the Windows PC, and therefore it doesn't really address those. And so I will say in something regarding the air-gap network, no matter how good your connectivity, how good your protections are protecting you from outside connectivity, invariably you still have a porous network. You still have a way of getting information onto that control network. Why? Because you still need to perform software patches, even antivirus updates, log management. There's still information that needs to come in and out. Now, what it may be, it would be a very low bandwidth channel. That may be because you burn CDs or use USB sticks. But ultimately, there is a communications channel from the process control network outwards. It's just dependent on how easy it is to utilize. So I would say at this stage, is this enough? This is typically where most people stop. They focus on the cybersecurity of their enterprise systems or their PCs within within the process control environment, but then leave it there. Why? Because they say, you know, we have endpoint protection from our PCs. But what about the PLCs? I just like to take a thought exercise, which is, why is there antivirus on a PC in a control network? The only reason for running antivirus on a control network PC is because you believe that malware is going to get onto that network. If you don't believe malware is going to get onto the network, then there's no requirement for antivirus. But taking it the other way, what about the PCs? The PLCs are also connected to those PCs, yet they do not have antivirus. But most people say, don't worry, they're behind a firewall, don't worry, they're in a process control environment, they don't need antivirus, they don't need any way of protecting themselves. But if that's the case, why do you have it on PCs? So, and most people sort of go down the logical thing of, well, I'll just block external access to any of their PLCs. I'll stop anybody being able to connect and communicate with them. But unfortunately, they're normally on one single or a couple of internal network LANs, or a very flat network. So what about unauthorized internal access? Can I go in and can I plug any one of my laptops in and start communicating? Does a contractor have the ability to come on site with a laptop to plug in to fix the problem, but essentially is plugging into your process control network and has the network connectivity to communicate with your PLCs and your PCs? The other thing is to say, well, we can't add in too much inline protection for the control network because we need to ensure availability. We need to ensure that we can always communicate at any time. But what availability also enables you to do is send malicious packets. You've basically created a system to allow me to send out one denial of service packet which will crash your network. One of the most common vulnerabilities we're finding at the moment, and if you scroll through the ICS CERT vulnerability database, what you start to see is quite a common occurrence of these denial of service attacks. Essentially, a malformed packet, a badly formed message, can be sent, and the controller, the PLC that receives that packet, when it tries to execute it, process it, it ends up causing an error, and it causes the system to crash, creating a denial of service. And that's generally because the protocol parser, the protocol implementation on the controller is not necessarily, it's not been designed to be reliable. It's designed to be reliable, it's not designed to be robust. What that means is if you tell it to do something in a legitimate way, it will do it very well. If you tell it to do something slightly different, well, it might fall over. The other aspect of this is ensure visibility. We have very good visibility of what is happening in the real world. All of the safety monitoring, the process monitoring that we have, we can tell exactly in any process what the temperature is, how fast things are spinning. We have very good situational awareness of the physical world, but we don't have very good visibility of the network. What is the messages going between the server and the controller, between the client and the server? What are the messages coming back? What are the meter readings saying? So we can see if we walk up to a meter, we can read it, the value, or we can read it in the HMI. But can we correlate the two and say exactly what is being sent is what is received? And then finally, the bottom one, response. Can you identify if something is going wrong, that it's definitively a component failure, that it requires repair, or it's a cyber attack? Because what we saw with Stuxnet, what we saw with other cyber attacks against control systems is you can make an attack look very similar to component failure, or start to impact the reliability of the system. Why? Because that preys on the operator's experience. We've historically been very aware of when things start to go wrong, when things start to break, oh, it's easy. What we can do is we can just walk up, we can replace the equipment, and we can carry on. And you start to identify and start to relate to it being a component failure, when in fact it's a cyber attack. So I'd like to end this with just a couple of questions and say, can you answer these 5 questions in your own system? Does your embedded device, and for an embedded device, we're really talking about PLCs, RTUs, anything which is a processor, but is not running Windows, is not running Linux, is not running a desktop system. Can your embedded device identify who is talking to it? It may receive a command, but can it definitively say who's talking to it? In the old days of control systems, we used to have direct wired serial links where you could say, I know exactly who's talking to me because they're the only person on the other end of this wire. Unfortunately, now with network systems, almost anybody can be communicating, and anybody can impersonate anybody else. So can your embedded device definitively say who is talking to it? Or does your device essentially trust everybody on the network? On the network, is it just the HMI who's allowed to send commands to the PLC? Or is it also a SCADA server? Is it an engineering terminal? Which computers on that network are legitimately allowed to communicate, and which ones are not allowed to communicate but still have the capability of doing it? Can your embedded device recognize when it's been sent a malformed or malicious command? Or do you rely on the vendor implementation on that control system? Has that PLC been robustly tested? Has it gone through a fuzz testing regime where you can test the reliability of the product and the robustness of the product? And then can your embedded device validate that the command it received was the command that was sent? Is anything in a man in the middle or did malware on a PC manipulate the command coming from the HMI? What the button that you pressed on the HMI, how do you know that that's the message that was received at the embedded side at the far end? And then finally, can you verify or audit what your devices are doing? Or do you just take it for granted? Do you just receive that the PLC will report what it's doing and you receive that message as if it's accurate and we go from there? So those are the 5 questions I really want you to ask yourself, because those are the 5 questions which, if it's going any other way, attackers can start to manipulate. I don't have to blow up a system. I can just start manipulating some of that information and causing some bad things to occur. So I would like to take this opportunity just to ask you guys again, sorry, I know there's a lot of questions in this presentation, but we're wondering is, on your embedded devices, can they validate the commands? Those 5 questions, are they capable in your system of identifying who's talking to it, what they're saying, knowing full well that what they are doing is actually what the operator intended for it to occur? Okay, thank you very much for participating in that. What I will point out is, wow, it's quite good. 57% of you says no, but I want them to, and 16% are saying actually yes. So between almost 70% of you are saying yes, that would be great. But what's very interesting is the bottom 24% saying no and unsure if needed. And I think this is a very valuable position to be in. And part of the rationale for having this webinar is to help articulate why we believe this is needed. We hope to take that 24% of you and reduce that down to much less, potentially 0. So at least you can not be unsure anymore, but at least have an opinion, at least know if it's yes or no. Okay, so what are the embedded vulnerabilities that are required in the system? First of all, who is sending commands? As you can see in the sort of little diagram, typically what should happen is a command should come from the SCADA server and it should go all the way down to the PLC. What in reality is if malware gets onto an affected machine, if malware gets onto a machine, it itself can start sending communications itself, and the PLC will not know the difference between the command it received from malware and the legitimate command it received from the SCADA server. If the PLC is unable to do that, then they can essentially do anything they like. They can impersonate the PLC, they can impersonate the PC and start doing bad things. The second thing, which is still, which is probably worse, is the attacker can actually introduce their own device. So it's not necessarily compromising one of the existing PCs, but it's actually introducing their own device into the system. Why? Because what I can start doing is, again, I can start injecting my own packets and I can start controlling the PLCs from my own computer. The way we normally mitigate this is by either using something like MAC address filtering, port authentication, or even SCADA firewalls. The idea is you shouldn't be allowed to connect any system which is unauthorized into the network. We shouldn't be allowed to connect a contractor's PC, shouldn't be allowed to connect in. I shouldn't be allowed to bring in my own Raspberry Pi and connect it to the network. So if we can limit the devices communicating to only being those legitimate devices, then we can at least start to control who can talk to our PLCs. But unfortunately, MAC filtering is not always that easy to implement, specifically because I can do a man-in-the-middle attack. I can easily spoof MAC addresses, and I can start injecting my own commands. Port authentication is pretty easily bypassed if I have a $5 network tap, and SCADA firewalls require a lot of configuration and management, and there's no, again, there's no authentication mechanism in there. So while you might be able to control exactly what somebody might be able to say, what type of communication they can say, you can't validate exactly who are they from. So is what I heard what I said? Again, a command will come from a PC all the way down to a PLC, and this is pretty standard. This is what everybody understands. However, an attacker can introduce their own device into the network, and what can happen? Well, they can perform a man-in-the-middle attack, which is I receive the will get in the way, and I perform an ARP spoof and basically tell the SCADA server, if you want to send a command, you have to send the command to the PLC. You have to send the command via my device, and my device will take that. I will manipulate the command, and I will eject it back onto the network. What this means is the command that was received by the PLC is not the command that was actually sent from the SCADA server or the HMI. And in the case of a SCADA firewall, this is going to go straight through the firewall because I haven't manipulated anything to do with the headers of the packets. I've just manipulated the contents of the message. So one way of doing this is to mitigate the ability to manipulate commands, you should use secure protocols. What we mean by that is those protocols which can have cryptographic authentication and cryptographic integrity protection. That is to say, the receiver can cryptographically verify who sent the message and that that message hasn't been manipulated en route. Unfortunately, there are very few protocols available in the industrial control community that supports this. Even DNP3, which has secure authentication, it's not available for all types of packets. It's only available for a subset of packets. And the other option is then to just use end-to-end encryption. By using layer 2 or layer 3 encryption, we can prevent anybody from being able to plug into the network because without the correct encryption key, they're not going to be able to communicate successfully. They also won't be able to manipulate any of the commands without breaking the, causing the encryption to become broken. The problem with using encryption is that actually there's key management issues. It's actually very difficult to perform. Encryption, you should never buy encryption for how strong the key is. You should always buy encryption based on how good the key management is. And anybody can do encryption, but it takes a very few who can actually do key management well. You also need to do independent validation. Just because somebody says they have done encryption doesn't mean they've done it right. You actually have to go away and have that independently validated because it's very easy to get encryption wrong. So the final vulnerability I'd like to discuss is it a valid command? Now this is quite important because this is the one, as I say, we're seeing quite a lot in the industrial control community, for DNP3 especially. Adam Crane was a great security researcher who's gone and fuzz tested a lot of DNP3 implementations and found one single malformed packet can crash a DNP3 outstation or a DNP3 controller. And what that means is just by sending in one slightly manipulated packet, I can cause a denial of service and take down your ability to do any sort of sense, monitoring, and control. So what happens here is a bad command comes directly from a SCADA server and crashes the PLC. Once the PLC dies, there's no ability to communicate, and I can keep sending it out to lots of other packets. The high availability nature of the network means that if I can send a bad packet that can crash your network, I know I have a reliable infrastructure of which to send that malformed packet. So there's not a lot of mitigations against this unless something on the network is able to fully understand and appreciate what are the dangerous aspects, be able to understand all of the protocols to a very fine degree and be able to identify those dangerous packets within that. So that's really, you can use a network IDS, but that's really signature only. As long as somebody has seen that exact type of attack before, they can write a signature to identify it. IDSs are also detection, not prevention. So they're not in line. They won't be able to identify when a bad packet is coming through and prevent it reaching the PLC and crashing it. It will just be able to identify and say, yes, I think I've seen a bad packet, and it probably has crashed the PLC. So the only realistic option is protocol parsing. That is, those capability to actually inspect the packet, make sure it is well formed, make sure it's a legitimate command, and that command should be sent at this time. For PLCs, it doesn't necessarily have to be a malformed packet. If I can send a rewrite firmware command, a legitimate rewrite firmware command, I can also cause damage. During normal operations, you should never rewrite the firmware on the PLC. But it's still a legitimate command, and most PLCs don't necessarily understand the difference between operational and maintenance cycles, and will be able to and will accept that legitimate command and start rewriting the firmware. The other issue with the protocol parsing is what happens when you detect something bad. How do you alert? Do you alert in-band or out-of-band? Now, for those who don't know, in-band management is management that occurs over the same channel as the normal operational data. And out-of-band is when it happens over a completely separate network. For many industrial control systems, you actually want to use out-of-band management so that any of your security alerts, any of your security management controls can all be performed over a completely separate network from your process control network, so that none of the security-related communications interfere with critical control communications. So we've talked a little bit about all of those different elements of what happens when malware gets onto a PC, what happens when somebody connects their own equipment into the network, what happens if a control system actually ends up intentionally sends out bad malware. So I was wondering, in somebody's system, do you implement additional security other than the basic enterprise security, or do you rely just on that enterprise security? Those vulnerabilities that we just went through all the way down to the embedded end, is that something which you guys have solutions for, or is that something that you essentially rely on the integrity of the PC enterprise network security? What's interesting that we've noticed here on the respondents is almost nobody has said yes, they do end-to-end security. Some people, a lot of people have said yes, we do some, but it's not everywhere, and only a few people have said no, they don't plan or want to, and they don't think it's needed. So, and how do you, for those people who say yes, we do some, but it's not everywhere, or those who say they want to do it, how do you go about implementing this? Sorry, I'm skipping through the presentation by accident. Okay, so what are the solutions? One of the the best type of solution you can go for is implementing IEC 62443. For those in the know, this is one of the pretty much the only full cybersecurity standard for industrial control systems. And it's a really comprehensive standard that can be used for a wide range of industrial control solutions. Typically, we have some standards already for available for different industries, but IEC 62443 is really a cross-industry standard. And its approach is what we've been advocating so far, which is a zones and conduit approach. The idea is to, instead of having one giant flat network where everything is interconnected, what they should say is group those assets which you're okay, we should all communicate together, but you don't want to have communicate with the outside world, and actually start controlling what information is allowed to come in and out. The way I like to look at it is anything within a zone, if an attacker gets in, you lose everything within that zone, but you don't lose anything between zones. So you can think of all those little red dots between the zones, all the conduit protections, essentially quarantine any infection, quarantine any impact to just being within a zone. This provides you with multi-layer security, We also advise multi-vendor security. It's very common to basically buy one vendor solution to provide the control equipment. The problem with having one vendor solution, especially for security, is if any one problem is the same as we have with Windows. If everybody is running a Windows machine and there is a Windows vulnerability, well, we have a single point of failure, a single vulnerability now that will affect everything in the system. The purpose of using multi-vendor security is the idea that at least if one protection fails, it won't be a class of problem that will exist across all of your security solutions. The other aspect, apart from following a good standards-based approach, is to basically ensure that using well-developed products. And I like to say reliable does not equal robust. When we go about purchasing vendor equipment, we typically look at mean time to failure. We look at the high availability. We look at how reliable is it. But we're less likely to look at how robust is it. How have you gone through fuzz testing? Have you gone through a vulnerability assessment? How easy is it for me to knock over your box? I mean, we remember the bad old days when just doing a simple ping sweep of a network would crash control systems. But now we can have a more sophisticated ping sweep, which will crash just as many pieces of equipment. So how can we ensure that the equipment that we're buying is well developed and robust? Ensure you demand security acceptance testing and support in your new contracts. This is very, very important. You are never as powerful as you are when you're negotiating a contract to begin with. Make sure you have good security language and good acceptance testing language in your documents, in your contracts. Finally, train your staff and test your staff. There's no point in just doing regular security awareness training without performing tests, real-life tests on both your staff and your system. Most people do penetration tests. You can do similar aspects of vulnerability assessments for industrial control systems. So we'd advise not only to train, but also to test. Trust but verify. And then finally, reality check. So we've talked a lot about this. Mike helped identify all the different potential attacks and some real-life use cases where they have gone ahead. And I say, would you target me? Do safety systems help? We've come across a lot of these concerns over the years, and we have identified there a few mitigations, a few sort of answers to those. But the very bottom point is something I like to dwell on a little bit, and that is, why isn't there more of this? People say, you know, I haven't seen this doesn't really affect me, nothing's really been in the news. The reality is, past performance is no indication of future results. And in fact, what we are seeing is there has been a rise in successful incidents. They may not be plastered all over the news, but as Mike will happily point out, there are many more of them. If you go to any Black Hat and DEF CON is about to kick off in Las Vegas next month, and there you can actually go on a couple of different control systems penetration testing courses. So they're teaching people how to go in and how to assess and attack control systems. Mike, do you want to jump in and answer any of these, provide any insight to this?
Well, I certainly wanted to get your information on the cyber fence, but I think you're right. We only presented a few use cases. There are lots of incidents that I'm aware of that have occurred that fall into all three categories that have had effect to control systems. But in particular, there's been emergence of some new targeted attacks where it's very clear capabilities are being fielded with good delivery techniques. We have not seen effect payloads in most of them. The German Ironworks is the exception. So people can think through their options.
Thanks, Mike. So I said that
Muted.
Provide you with takeaways just before we signed off and went to questions. So if I could have you just think of 3 things as takeaways before we leave. The first would be ICS cybersecurity has to be more than PC and network-based security. We see time and again that there are different ways of bringing physical equipment on site, be that contractors' laptops, or even sorry, my slides seem to be running away from me. Trying to go back one. There we go. So if you went to a conference, S7, Stephen Hilt provided a great introduction and demonstration showing how you can put a Raspberry Pi and a cell phone into an RTU, into an actual RTU frame, and put that into the backboard, essentially assuming that nobody's going to notice the difference between the PLC module, the I/O module on the left and the I/O module on the right. They've now started to hide them in power supply cords, so nobody checks on the desk to make sure that their power strip isn't also plugged into the computer. We have people from ShmooCon actually embedding a wireless receiver in a USB cable. So the idea that malware is only going to come in, or an attacker is only going to come in via software and via software loads, has been sort of blown out of the water. Now there are definite hardware attacks, there are definite hardware methods of gaining access to your system. So apart from just relying identifying that security is more than PC and network security, you have to also demand implementation of security from end to end. You have to assume that the network, that the devices on this network, that your process control network is not as integral, is not as safe and secure as you think it is. So secure, if you have security end to end, you can authenticate who's talking, you can protect what's being said, and you can control what is allowed to be said and prevent malformed packets. And finally, as we said, reliability does not equal robustness. So as I said, just before we open it up to questions, this is obviously an Ultra Electronics sponsored talk, so we'll talk a little bit about our product. It's the CyberFence ICS system, security system. So I'm just trying to the slide again. Perfect. And it's essentially a small inline encryptor, deep packet inspection, and firewall device. Essentially what it can do is provide for those legacy systems or those initial existing deployments which have no security. It can be bolt on and provide all the encryption necessary, all of the firewall necessary. It has full protocol support for different protocols, including DNP3, for Modbus, for Ethernet IP, and for OPC. So we can validate exactly what is being said and make sure that there's no unauthorized malformed packets. It can also control what is being said, so you can limit the right commands during normal operations. You can prevent firmware updates. You can prevent any unauthorized, illegitimate commands, even if it's from an authorized source, while the network is ongoing. And apart from that, it's actually the only ICS security product which has gone through independent validation. That means we've taken it to a lab. You shouldn't just trust us. It's actually taken it to government labs to make sure the encryption is done correctly. This cybersecurity functionality has been done correctly through common criteria. It's been penetration tested by a number of different independent penetration test firms. It's been gone through fuzz testing. So all in all, the whole idea is it's a robust, independently validated solution that can provide that end-to-end security and that real protection that is lacking in a lot of control systems. So I appreciate you spending the time and making it through the whole presentation. We'll now happily open up to questions.
Unmuted.
Folks, at this time, if you have questions, please enter them into the questions window. We will answer them momentarily. Alex, our first question is, what percentage of cyber threats would end up being a disaster for a company's infrastructure and also causing physical damages? What can it be the best possible countermeasure against them?
I'm sorry, you broke up at the end then. Could you repeat the question?
What percentage of cyber threats would end up being a disaster for a company's infrastructure and also causing physical damage? What can be the best possible countermeasure against them?
Well, that's very difficult to say. I don't know if we can put an exact number on the different types of threats, but what we are definitely seeing is a more concentrated threat approach to ICS security. That is to say that we're moving away from the PC-centric cybersecurity and moving actually into the industrial control specific security. Why? Because it's easier. It used to be that hacking PCs used to be a lot easier to do, but Microsoft has done a great job in actually beefing up the security of Windows. So it's actually now very difficult to get on and attack the Windows side, the enterprise side of your industrial control system. However, the PLCs, the embedded side, is still the soft underbelly. It's still incredibly easy, and we do workshops all the time where we bring on real industrial control equipment, and we go in and start manipulating packets. I remember working with one cybersecurity vendor to create a workshop for a customer, and the customer said, yeah, this is all very good, but that's with other people's products. Can you just do something with our products? And so we thought about it, and we said, sure, give us 2 days. And we went away, and within 1 day, we basically fuzz tested their control equipment, and we found a packet which could quite easily, which did take down their system. And so we went back in the next day and performed the same workshop, only this time using their control equipment. And we weren't really phased by anybody else's using a new piece of equipment because it's so easy now to attack them. So I would say the difficulty with just relying on enterprise security and the difficulty looking back at previous trends, it doesn't necessarily take into consideration new approaches, what the attackers are now doing. So if I could offer one piece of advice of something to do, it's really to take as fact that your process control network is not as clean as you may think it is.
Unmuted.
Next question is also for Alex, but Alex, Mike, feel free to chime in. Are there any resources for security acceptance testing requirements we can use in SAT and FAT?
Muted.
I believe IEC 60443 and ISA Secure has good language that you can sort of take out and implement. If you've come across the ISA Secure vulnerability, ICS Secure program, it's a way to ensure the robustness of equipment and systems and independently validate those. And I believe that has some really great language in it to help lift out and put into your own contract language. But Mike, maybe you can chime in.
No, Alex, that's a great response. I was about to say IEC 62443 has a wealth of resources and language that could be modeled. Also, though, the Department of Homeland Security and the Department of Energy both created procurement guidance, which includes language that includes measures that you could put not only in the RFP into the contract, but also measurements that you could track it through the testing regime through FAT and SAT. So those are also very easily available references and resources. So both the DHS ICS CERT webpage will, under their resources, and the Department of Energy has a page dedicated to energy system procurement language.
Unmuted.
I said it ultimately comes down to the reliability of the network. And the reliability that's
Muted.
if your contractual language has an uptime or a high availability language in it, there is an element of cyber associated with that. And it would certainly be of interest, those people who have already gone through the contractual stage and already have existing contracts to look at the language and maybe sit down with your in-house lawyers and determine, does a cyber attack which affects the availability of the system, does that negatively impact the vendor's performance?
Unmuted.
And with that, we are unfortunately out of time. So thank you so much, Mike and Alex, for your great presentation, and to Ultra 3ETI for your sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, you can visit sans.org/webcast. Until next time, take care, and we hope to have back again for the next webcast.
Thank you. Bye, everyone.
Muted.
Thank you.